there's plenty of time for questions.
Okay, great.
Also, Tracy, just so you know, the shared screen is on the YouTube website instead of the slide.
Okay.
Okay, give me just a second. Let me see what happens here.
Sure.
Is it back up, Katie?
Yeah, now it's back.
Okay.
But yeah, I think that's a good balance, Lantao, because we do want to leave some time for questions. So,
Yeah.
And you know, some people have other meetings like at noon, so we don't want to, you know, go too long or anything.
Sure. Ooh.
Welcome, everyone. We'll get started in a few minutes. All right. It's 11. Are you ready to get started, Lantao?
Yeah.
Okay. So welcome everyone. Thank you so much for joining us this morning, especially today on Election Day in the US. I hope everyone who wanted to was able to vote safely or is able to vote safely today. So I'm very happy to introduce Dr. Lantao Sun as our seminar speaker today. Dr. Sun is a research scientist in the Department of Atmospheric Science at Colorado State University. He received his bachelor's and master's in atmospheric science from Peking University in 2002 and 2005, and he received his PhD in atmospheric dynamics from the University of Illinois in 2010. He was a postdoctoral fellow at Cornell as well as here at NCAR before joining Ceres and NOAA as a research scientist in 2015, where he worked until joining CSU in 2019. His research interests include climate variability and change, subseasonal to decadal prediction, and Arctic mid-latitude linkages. So today he will speak about uncertainty in the winter atmospheric response to Arctic sea ice loss, the role of stratospheric internal variability. So take it away, Lantao. We can see your slides. You might want to put it into full screen mode.
Okay. Does this work?
Well, this works. We can still see the sort of preview on the side if you want to put it.
Okay. I suppose I should change it a little bit. Let me see how. Give me a second. Maybe. So is that the same?
It's the same. So there's a button at the bottom that usually puts it into presentation slideshow mode that you could use, or I think you can go to the slideshow tab.
Oh, let me see. Because I at this moment I couldn't see that. I see use slideshows, but my mouse doesn't work there. It's a little bit weird here.
Yeah, do you want me to share, or this is okay and the slides are just a little bit smaller, but as long as you can see them. Oh, that looks better. Yeah.
So does this work?
Yeah, this is working. Yep.
Okay, perfect. I see the slideshow now. So let's see. Okay, thank you, Katie, and good morning, everyone. So glad to have this opportunity to share some results from the polar amplification map. This project, I'm collaborating with Clara Dancer, and also when I run this polar amplification map experiments, I got a lot of help from NCAR colleagues. So really appreciate that. Now let's go to some basic context. Arctic sea ice is melting rapidly, and this year marks the second lowest Arctic sea ice extent on record. And also climate models forced by the increased greenhouse gases have projected that the Arctic Ocean will be seasonally ice-free by the middle to later this century. So one interesting question to ask is, how does the sea ice loss will affect our climate? So far we already know that sea ice loss is very important for the Arctic amplification, and sea ice loss also can increase the precipitation over the Arctic and also cause more opaque clouds in the autumn. But it's still not very clear how does the sea ice loss will affect the lower latitude. One example for this is this so-called warm Arctic cold continents paradox. So the figure here is from the observed DJF surface at temperature trend over the 1990 to 2013. If you look at this like 24-year trend, you can find a strong warming over the Arctic, which coincides with the cooling trend over the Eurasia and North America. And some studies have suspect that it's Arctic change that drives the mid-latitude cooling. But there is some causality issue, and this hypothesis has been challenged by other studies. Nevertheless, this hypothesis has motivated a lot of recent empirical and modeling studies to understand the Arctic sea ice loss effect. In particular, if the sea ice loss is causing cooling over mid-latitude. So just to show you some model results. So in North America, the story is a little bit simple because as far as I know, several modeling studies have found that the sea ice loss is causing winter warming and less cold extremes in North America. But it's a little bit controversial in the Eurasia because some modeling studies found that sea ice loss is causing more Eurasian cold winters, while others do not. I'll give you one example here, which is on the top panel. The left is from the Maria et al. Paper, who have done some Arctic sea ice loss experiments. And the figure here is the temperature and sea level pressure response to the sea ice loss in the Barents-Kara Sea. You can see a strong warming in the Barents-Kara Sea there, and also causes cooling over the Central Eurasia, that black box. And on the right panel, I also have this figure from our 2016 paper and plot in the same format. You can see we do the similar experiment and also found the warming over the Barents-Kara Sea, but we didn't see any cooling over the Central Eurasia. So whether this reflects model deficiency or not is still debatable. And sea ice loss can be also related to the polar vortex. So because right now there are two types of polar vortex discussed. Here in this talk, when I say polar vortex, I only talk about the stratosphere polar vortex. And the stratosphere polar vortex is connected to the surface through this northern annular mole. So the right panel just from this Thompson and Wallace classic paper gives some feature of the northern annular mole. Basically, when the stratosphere polar vortex is stronger, you will expect the near surface circulation to be in the positive phase of the NAM, or North Atlantic Oscillation, NAO. And when the stratosphere polar vortex is weaker, the near surface circulation will be in the negative phase of the NAM or NAO. And the stratosphere becomes relevant because some recent studies have found that the sea ice loss in the late autumn can cause weakening of the polar vortex and subsequently the negative NAM and the NAO in winter with the cooling over the Eurasia, as shown in the top schematic graph. However, we are still not certain of that because some observational analysis does not support this stratospheric pathway. And also some other studies suggest that it's a Euro blocking that can cause weakening of the polar vortex and also the sea ice loss. So in other words, it's the stratospheric pathway of Euro blocking, and the sea ice loss is just a side effect. And furthermore, some other modeling studies found that winter atmospheric circulation response is caused mainly by winter, not autumn CS loss. This also poses some challenges for the stratospheric pathway because stratospheric pathway mainly argue the autumn CS impact on winter circulation. And I will talk a little bit on the model consistency and the discrepancy here. So far, you probably have the impression that the Arctic CS loss impact is very model dependent. That is true because the CS loss impact on atmospheric circulation has a low signal to noise ratio. But that's not completely true because when the CS forcing is large enough, like the end of 21st century, like 2080 to 2099, so when the CS forcing is large enough, you can see some robust features in different models. And one example is shown on the left figure, gives you the sea level pressure response to end of 21st century Arctic CS loss in 6 different studies. And you can find a lot of robust features, actually. And by contrast, the atmosphere response to observed Arctic CS loss is very model dependent. You've already seen some results earlier in the slides. And I also want to mention that multi-model experiments generally show very little atmospheric circulation response. And these model discrepancies cause a lot of issues for us to really understand the Arctic CS loss effect, because it's really hard sometimes to reconcile different studies. Normally different experiments, they have different CS forcing, or different ways to impose the forcing and some other differences. So it's really hard to understand why these different model simulations are given different results. So that's why these coordinated model experiments are so useful. By following the same protocol, it will be good to have this model comparison and really understand the model sensitivity to the Arctic CS change. And here, just to give you a quick overview about the polar amplification and the experiments we will discuss here. So polar amplification, the goal is to PA map, the goal is to investigate the causes and the consequences of polar warming. And PA map has proposed several different types of experiments to investigate the Arctic CS loss effect. In this talk, I will only focus on the time slice atmosphere model experiments with the NCAR CAM6. And these are shorter runs, so 14-month simulation with a year 2000 radiative forcing. And the only thing changed is the Arctic CS concentration, which can be prescribed to pre-industrial, present day, and future conditions respectively. And the thickness is always set to be 2 meters everywhere in the Arctic. And there are 200 member ensembles, which is constructed by the perturbation method, which is a micro perturbation method. Actually, for the ensemble size, PA map recommend 100 members, but some recent studies have found that that might not be enough. For example, this work by Jack Lab has estimated the minimum ensemble members needed to look at the Arctic CS loss using the NCAR's YCOM4 model. And according to his study, for the circulation variables, the minimum ensemble members will be generally around 150 to 200. So initially we run the simulation for 100 members, then we extended to 200. I will talk about this in more details later in the slides when discussing the internal variability, but I thought it will be good to give you a context here. And the figure here is for the CS concentrations for the pre-industrial, present day, and future condition. The pre-industrial and the future Arctic CS condition both come from the models, the CMAP5 pre-industrial simulation, and the CMAP5 future projections with the global mean temperature to be 2 degrees above the pre-industrial period. So if we consider this future CS loss, it's around the middle of this century. And there are actually 7 different simulations, because for the each CS condition, we can set the global background SST to be different conditions. For example, for the pre-industrial CS condition, the global mean SST can be set either to pre-industrial or present day. And similarly, for the present day CS condition and the future CS condition, so that we have totally 7 simulations, each 200 members, which will give us 1,400 ensemble members. And from that, we can isolate 4 different CS loss results. And they are for the past CS loss, which can be calculated by differencing the present day with the pre-industrial, has the pre-industrial SST condition and present day SST condition. And similarly, the future CS loss effect also has one for the present day background SST and one for the future background SST. So in that way, we can examine, given the same CS loss, whether there is any sensitivity to the background SST and the basic state. And now let's look at some of the mean atmosphere response to Arctic CS loss. So in this case, we average over the whole 200 members. So the figure here is the monthly evolution of the past and future Arctic CS loss shown in bars, and the Arctic average surface energy flux response in curves. And the left y-axis gives you the magnitude of the CS loss, and the red bars and blue bars is for the future and past CS loss. And the red curve and blue curve gives you the future and past surface energy flux response over the Arctic, and the red y-axis gives you the magnitude of the surface energy flux response. We can see that the Arctic CS loss is largest in autumn, specifically from August to November and December, but the surface energy flux response is peaks in winter around December. And also the surface energy flux response to future CS loss is larger than the response to past CS loss, because the ice loss is larger in the future. And we can also compare the 2 different background SST cases and found there is very little sensitivity to the background SSTs. And next, we can look at the Arctic surface temperature response. And we found that it well follows the surface energy flux response, showing the very similar seasonal cycle. And how does the Arctic sea ice loss affect the lower latitude? To show that, here we have plotted the seasonal surface and temperature response to the past and future sea ice loss in shading, and overlaid by the sea level pressure response in contours with a contour interval to be 0.5 hectopascal, and the red contours shows the positive values and the blue contours shows the negative anomalies. The staplings give you the 95% statistical significant level based on the student t-test. And I should also mention that because we don't see much sensitivity to the background SSTs, so in this case, we just combine two background SSTs for the past CS loss and the future CS loss, so that each of them have 400 member average mean. And look at the temperature response first. Mostly we see CS loss is causing warming over the continents, and the warming is smallest in the summer season and largest around December. So we see a lot of warming in the autumn and winter. We can also look at the atmospheric circulation response, particularly look at the autumn and winter season. In the OND season, what we see is mainly the regional loss. So this can be understood as a direct sea level pressure response to the surface warming, because when we look at the vertical circulation response, it's mainly showing this loss near the surface and high above. So this baroclinic pattern is generally understood as the direct response to surface warming. And then we can look at the winter circulation response. We can also see some lows, especially over the Hudson Bay, but the pattern overall are more complex than the autumn circulation response. So to better understand the GFM season response, we have put the response here, showing the response to the past CS loss on the left and the future CS loss on the right. Also, I give the numbers for the past CS loss and the future CS loss in winter. And you can see the circulation response pattern share some similar features. And also, we can also look at compare the temperature response. So firstly, look at the North America. So we can see we found more warming in North America in the future CS loss case than the past CS loss case, likely due to the increased ice loss in the Hudson Bay. And we can also look at the circulation response over the Eurasia. This red contours in the past CS loss case means strengthening of the Siberian high, and it becomes larger in the future Arctic CS loss case. And because of that, we also found a little bit of cooling in the Central Asia, which presumably is a result of this strengthening Siberian high, which bring more cold air into the lower latitudes. And also we can find a little bit of strengthening of the Aleutian low in the future CS loss case, but not much in the past CS loss case. So the question we ask here is that, is this circulation response pattern a robust feature to Arctic sea ice loss? And we only have two cases, so it's really hard to compare, but we have done some experiments before. So I just put it here. This is from our 2015 paper, in which we have the end of 21st century sea ice loss. You can see the numbers almost double the future sea ice loss case in PA map. And again, we can compare the circulation response and surface air temperature response. We found very similar features, including this strengthening of the Siberian high, and it becomes even larger. And look at the temperature response. This, because the strengthening of the Siberian high is even larger, it causes a little bit of even more cooling over the Central Eurasia. And also the Aleutian low strengthening also becomes larger, but over the North Atlantic, the NAO response does not increase in these simulations. So overall, for the PA map experiments, we found it's overall it's a warming impact. We don't really see much cooling. Because of that, we have averaged the continence temperature response over 50 forward, and also get the seasonal cycle of the temperature response to Arctic sea ice loss on the bottom panel. You can see again it well follows the seasonal cycle of the surface energy flux response. How about the precipitation response to Arctic sea ice loss? Here I show the precipitation response to past and future sea ice loss for different seasons. Again, we look at the autumn season and the winter season, found that the signal mostly in the Arctic, showing increased precipitation in the sea ice loss region. And outside of the Arctic, there are not much signal. The only signal is over the North Atlantic. In the Mediterranean region, we see a little bit increase in both past and future sea ice loss, which likely related to the negative NAO, but overall it's weak and sometimes not statistically significant. And then we can do the same thing by average the precipitation response over the Arctic, and showing it on the bottom left panel. Again, you see this very similar seasonal cycle of the precipitation response. It suggests that the surface energy flux response actually is the key to understand the atmosphere response to Arctic sea ice loss. So next, let's look at the internal variability. As you may recall, we have conducted 200 member of simulations, while the PA map only recommend 100 members. So it will be interesting to look at the response average over the first 100 members and the second 100 members to see if there is any difference in the circulation response. And that's what we did here, and we purposely pick this past sea ice loss with pre-industrial SST, and I will also mention the other 3 cases later in the slides briefly. So what I show here is the zonal mean, zonal wind response in the winter season as a function of latitude and pressure in shading, and the contour is for the climatology. You can see it's mainly in negative values, means weakening of the westerly. This is actually expected because the Arctic warming will reduce the meridional temperature gradient. From the thermal wind relationship, we will expect there will be some zonal wind deceleration over high latitude. And the stratospheric response also tends to show some weakening of the polar vortex, but overall the magnitude only around 2 meters per second, so it's not very large. And then we can look at the average response average over the first 100 members and over the second 100 members. I don't know what you feel when you see these results, but when I first see these results, I cannot believe that they are from the same simulations, because they are nothing alike between these two 100-year averages. For example, if we look at the stratosphere, we got this weakening of the polar vortex in the first 100 member averages, and we got a strengthening of the polar vortex in the second 100 member averages, even though it's not statistically significant. And also look at the tropospheric circulation. The first 100 member average response can project onto the negative NAM, while we don't see much systematic signal in the second 100 member averages. And since all members, they have the same as forcing, such difference must come from the internal variability. And the question we're asking here is that, is the internal variability in the stratosphere polar vortex connected to the tropospheric circulation response? And to understand that, we need to first characterize the stratospheric polar vortex internal variability. And what we did is to use bootstrapping, and we can randomly pick 100 members and get the zonal wind response at 10 hectopascal and 6 degrees north. This is generally the latitude and pressure used to characterize the polar vortex strength. And then we repeat this 1,000 times to get the probability density function of this polar vortex response, as shown on the red panel. So you can see two horizontal bars give you the ±1 standard deviation and ±2 standard deviation. And the vertical red lines is the zonal wind response in the first 100 member average response. And the vertical blue lines is the zonal wind response averaged over the second 100 members. And you can see those responses are a little bit beyond 2 sigma, but it's not far from that. So it's not that super extreme. And then we wanted to understand how does this stratosphere polar vortex internal variability will affect the tropospheric circulation response. To do that, note that we have 1,000 times of stratosphere polar vortex response, and we can regress the tropospheric response onto the this polar vortex response and define it as the polar vortex index, and examine how much the polar vortex can explain the tropospheric internal variability. And give you one example here. This figure shows the zonal wind response at 6 degrees north, which is very close to the jet latitude in the stratosphere. And the left panel is the first 100 member average zonal wind response as a function of mass and pressure. And the middle is the average response over the second 100 members. And the right panel is the difference. Now you can see the first and the second 100 members show very different response. And their difference in response showing this weakening of the polar vortex in January and February, then showing this extend downward to the surface, which gives the largest signal in the February and March. And we can also look at the regression onto the polar vortex index. This showing the left panel showing the polar vortex response. It's -2 sigma, and the middle is the polar vortex response. It's in the +2 sigma, and then it's the difference. You can see that it can well reproduce the first 100 member average response and the second 100 member average response, and their difference also showing this weakening of the polar vortex with downward extension onto the surface. And in the bottom right panel, we also show the correlation with the polar vortex index. You can see in the stratosphere, the correlation is about 0.8, and the near surface is above 0.5. So this does indicate a stratosphere polar vortex internal variability can affect the stratosphere and the troposphere circulation. And now let's look at the tropospheric circulation response averaged over the first 100 members, the second 100 members, and their difference. We can see the first 100 members shows us some kind of a negative name, NAO pattern, which gives us a positive anomaly over the Arctic and a negative anomaly in the southern part. And by contrast, the second 100 member shows a very different pattern. We don't see much in the Arctic, in the upper levels, and near the surface, it's the negative values over the Arctic, which very contrast the positive values in the Arctic in the first 100 member average. And their difference is somewhat project onto the negative face of the name NAO. And we can also look at the results when we regress the response onto the polar vortex index. And overall, we can see that it can well reproduce the first 100 member averaged response and the second 100 member averaged response. If we go back and compare with that, we see it's very similar, and that difference which will project onto the negative face of the NAO on NAM. And I should also mention that when we compare the difference of the regression with the difference in response, we see that they are not identical, especially over the North Pacific and North Atlantic region. So this suggests that in addition to the stratosphere polar vortex internal variability, the troposphere also has its own internal variability, which may have nothing to do with the stratosphere changes. And the stratosphere polar vortex internal variability can also affect the surface climate response. The figure here, the top panel shows the surface air temperature response to the Arctic sea ice loss in the first 100 member average and the second 100 member average, and their difference in shading, and the contours gives you the sea level pressure response. And as you can see, look at the Northern Eurasia in the first 100 member averages, we don't really see much warming, and we even see some cooling, even though it's not statistically significant. By contrast, look at the second 100 members, we see a lot of warming over the Eurasia, and that difference gives us this cooling over Northern Eurasia, which likely related to this circulation response. And in the bottom, it gives you the regression onto the polar vortex index. Again, you can see that there is lack of warming over Eurasia, Northern Eurasia, and a lot of warming over the Northern Eurasia for the +2 sigma. And there are difference showing this cooling over Northern Eurasia, which also related to this negative phase of the NAO on NAM. And also we can look at the precipitation. The precipitation signal is mainly over the North Atlantic. For example, look at the first 100 member averages. We can see this meridional dipole with withdrawing in the northern part and widening in the southern part, and it can well reproduce in the regression onto the polar vortex. And for the second 100 members, there's not much going on, and similarly for the regression. And that difference, again, showing this meridional dipole, and it's again well reproduced in the regression, and which is related to this negative phase of the NAM and NAO. And so far you might wonder what's causing the stratospheric internal variability. So the stratosphere polar vortex can be modulated by the upward wave propagation from the troposphere to the stratosphere, so that when there is more upward wave propagation, we will expect a weakened polar vortex. And when there is less upward wave propagation into the stratosphere, we will expect a strong polar vortex. So the figure here shows the eddy heat flux response to CS loss at 100 hectopascal. This variable generally acts as an indicator for the upward wave propagation. And we can see that for the first 100 members, we see positive anomalies in the early winter. So this means that there will be more upward wave propagation from the troposphere to the stratosphere, which will cause weakened polar vortex. And by contrast, the second 100 member averages showing somewhat negative values, and this means less upward wave propagation into the stratosphere, and which will cause the strengthened polar vortex. And you may also wonder why the upward wave propagation will changes in the first and the second 100 members. And this can be explained further by the theory called constructive and destructive wave interference. I'm not planning to show more details here, but I just mentioned that briefly, that this more upward wave propagation is related to the constructive wave interference for wave number 1, while this less upward wave propagation related to the destructive wave interference in wave number 2. And next, I will try to summarize the polar vortex stratosphere, polar vortex internal variability. And you have seen the left panel for this past CS loss with a pre-industrial SST case. And here I show all the 4 CS loss cases. And firstly, you can find that for the first CS experiment and for the third experiment, the first 100 members and the second 100 members are very different in these 2 cases. Well, for the second case and the fourth case, we don't see much difference between these 2 100 members. This suggests that, so for these 2 cases, they're different, but these 2, they are not different. However, when we look at the distribution, look at the PDF in these 4 experiments, they show very similar distribution. This suggests that a similar stratosphere polar vortex internal variability is working in all 4 cases. Whether we see difference between the first 100 members and the second 100 members, it's just by chance. And we can also look at how does the stratosphere variability, internal variability affect the troposphere NAO response. So the bottom panel here shows the NAO response in the first 100 member average and the second 100 member average. And we can look at the first and the third case in which the first 100 member and the second 100 member show very different polar vortex response. And in this case, the NAO response in the first 100 member and the second 100 member is also very different. And by contrast, for the second and fourth cases, the stratosphere polar vortex are very similar, show very similar response, and the tropospheric NAO response also very different. But more importantly, again, look at the gray shading in the bottom panel, which gives you the 2 standard deviation uncertainty range associated with the stratosphere polar vortex internal variability. They show very similar range. This suggests that the similar stratospheric polar vortex internal variability are modulating the troposphere NAO response. And this is the last part. I will talk a little bit on the implications. And the first implication is that the internal variability is a function of ensemble size. This is probably obvious because we know that here we have used this bottom formula to calculate the internal variability in the stratospheric polar vortex and the surface NAO. It can be calculated by using the interannual 2 standard deviation times square root of 2 by considering a pair of experiments, and then divided by the square root of sample size. And the black curve gives you the estimate based on reanalysis, and the red curve is the estimate based on the CAM6 model. And you can see that it becomes smaller as the sample size increases, and there is a very good match between the model and the reanalysis. Just to give you some ideas about how large it is. So for the 100 members, we can get the 2 plus minus 2 standard 2 sigma to be around -3 to 3 meters per second. So we still got like a range of 6 meters per second in the stratosphere polar vortex response, which can sometimes influence the tropospheric NAO response, as we have seen previously in the slides. And the red panel gives you similar thing, but for the NAO 2 sigma and also the NAO response associated with the stratosphere polar vortex internal variability. And note that when we run UF to get the NAO time series, we have to standardize first. That's why for the model and the reanalysis, they always match each other when we look at the 2 standard deviation of the internal variability. And for the uncertainty associated with the stratospheric polar vortex internal variability, they are overall similar, and we see a little bit slightly larger value in the CAM6 than in reanalysis. And the second implication is regarding the observed trend. So the question you may ask is stratospheric internal variability relevant to the observed trend? So to demonstrate that, here we have plotted the time series of the DGF zonal wind at 10 hectopascal and 6 degree north. Again, it's a polar vortex latitude. And from the 3 reanalysis. So overall, after 1966, they match each other pretty well. And if we look at the trend over the whole period, we got a very small trend. So suggest that there is not much external force. And if we look at a little short period, like a couple of decades, for example, here for 1990 to 2010, we do found a trend around -5 meters per second per decade. And if we extend it longer to present day, these trends largely disappear. So it's likely the internal variability, but this trend could contribute to the sea level pressure trend. As shown on the right panel is the sea level pressure trend over these 21 years contributed from the stratosphere polar vortex. You can see this familiar negative NAO pattern. And actually, we can quantify how large is the internal variability by using the interannual variability using this method developed by Thompson et al. Paper and Clara's 2017 paper. So the left panel gives you the sea level pressure trend over this 21-year period. And the middle column gives you the 2 standard deviation of the NAO. And the red column gives you the 2 standard deviation for the stratosphere polar vortex internal variability impact on the sea level pressure. And the top panel is based on the reanalysis, and the bottom panel is based on the model CAM6. And we can see that they match each other pretty well. And more importantly, when we get some trends, we should always keep in mind that the internal variability is very large, even the part that associated with the stratosphere. And lastly, I will briefly talk about how to compare the model CS forced response with observed internal variability. You may recall that in the PA map, the past CS loss is calculated by using the observation minus the pre-industrial simulation from the model. So it's a little hard to find the exact match in observations, but we can approximately find that the linear change from 1970 to 2019 gives very close the CS loss to the past CS loss. You can see the numbers are very close over the winter season, and there is a slight difference in S loss distribution, but overall they are similar. And based on that, we can actually calculate this sea level pressure trend over these 50 years in January, February, March, contributed by the Arctic CS loss, which we can get from the PA map past the CS loss experiment, as shown on the left panel. And we can follow the same method to estimate what's the internal variability in the NAO for the sea level pressure trend, and also what's the internal variability from the stratosphere polar vortex. And again, very similar estimate for model and observations. And more important is that if we do this comparison, we will find the forced Arctic CS loss is much smaller than the internal variability. And even we only consider the internal variability from the stratospheric polar vortex. And however, there are two open questions. The first question is, do climate models overestimate the internal variability of the NAO? This point is raised by a recent Smith et al. Paper and also some other papers on this signal to noise paradox. So the idea is that a lot of the internal variability in the observations we estimated here actually could be driven by the surface lower boundary forcing. So in that case, we will overestimate this internal NAO. And in that case, the model here, which the internal variability model is purely driven by the internal variability, will overestimate this internal part. And in that case, this part probably will be smaller in reality. And the second question, which is probably a little bit more debatable, is do climate models underestimate the Arctic CS loss effect in Eurasia? And this argument is made by Murray et al. Paper and also replied by a Screen and Blackpot. You can find more details in these papers. And if this argument is true, it will mean that the CS loss effect shown here will be larger than what's shown in what's shown here. But I have to say that this part is very debatable, so we are still not sure of that. And this is the last slide. I just summarize the Arctic CS loss effect in the PA map. I think I don't need to talk about them here. I will just leave it here and take any questions. Thank you very much.
Thanks very much, Lantao, for that nice talk. If you have questions, you can type them in the chat, or you can use the raise hand feature, which is in the participants window. Question from Isla, go ahead.
Hi, thanks for the nice talk. I was wondering if you could go back to the 4 PDFs that you showed.
Yeah.
I'm just trying to get my head around the probabilities and kind of how unlucky or lucky you might have been to.
Sure.
So I guess you've taken 2 100-member samples and they've both happened to be on the extreme ends of the distribution for the left-hand one. And so like if they're beyond, say, the 5th percentile, you would want to, the chances of, I guess, having that happen twice would be 5% times 5%, right? Which would be a 0.25% chance, I think. And you've had that happen twice. It seems like having like 2 100-member samples be on the extreme ends twice is like a really unlikely thing to happen. I guess I'm wondering if you plotted this in terms of differences between 100-member differences instead, would the differences be extreme?
I'm sorry. Can you repeat the last sentence? What do you suggest?
So I guess I'm suggesting like taking the difference between the blue and the red line.
Yeah.
And bootstrapping based on differences. I feel like the difference is very extreme, right?
Yes.
You're very unlikely to get that large of a difference.
Right.
And you've had that happen twice. And so it seems like, I mean, you need to work out the numbers, but I feel like what you're seeing here has about like a 1 in 5,000 chance of happening. Is that fair to say, do you think?
I think this is a good point. I'm also like when I got this result, I'm also a little bit surprised, like why it happens a little bit too extreme. But I feel like it does happen, and the case that I show mainly this past CS loss with pre-industrial SST case. It's a little bit beyond 2 sigma, and the shorter case a little bit, inside 2 sigma, but overall they are very large. But it will be good if you have any suggestion to see like why it's so extreme, because the other 2 cases we don't really see much difference between the 2 100 members, and I'm also trying to figure out like what could be the reason. One thing I think I can rule out is that the first 100 members and the second 100 members they are something changed. I can rule out that possibility because I have tried to like rerun one case in the second 100 members and then using the per-lane value from the first 100 members. In that case, I can exactly reproduce the first 100 member case. So I think nothing changes, but regarding why this extreme thing happens, I'm not totally sure. I will be happy to listen to any possible suggestions for me to look at.
Yeah, I mean, it could just be chance, I guess, but it seems like it's worth quantifying what the chances are of having this happen twice.
Yeah.
And that it may be a 1 in 5,000 chance.
Yeah, I agree. I agree.
Okay, thanks.
Thank you.
Other questions? I guess I'll ask you, Lantao, at the beginning you talked about how coordinated model experiments are really important for understanding these, model differences.
Right.
And you posed some open questions at the end. Have you thought at all about, additional coordinated model experiments that would be helpful to answering some of these questions?
I think by looking at other models, it will be super useful to understand what's causing the difference between these different model studies. Like for example, at the beginning of the talk, I showed this this Murray et al. Study, and also the our own paper in which we don't find any response. So it will be good to to compare their PA map results with what we have here. And actually, I have a quick look at their response. So this is the PA map experiments, the future CS loss experiments in the Chem 6. And the bottom is from Murray's recent talk on their model. In this case, we are following the same protocol. And we can see if the model will still show some cooling over the Eurasia. And as you can see, in their Morocco model, they still got this cooling over Central Asia. And in our case, we only have very tiny cooling, but it's statistically insignificant. It's likely related to the circulation response here because their sea level pressure that high extend even southward, but in Chem 6 it didn't. Why is that? I think we probably need a little bit more model comparison. And this is just one example. I believe if we can have like 10 models or 15 models and have this comparison, we will definitely can gain a lot of useful information to understand the model sensitivity to the Arctic CS change.
Great. Yeah, thank you. Isla, did you have another question before we wrap up?
No, I forgot to unraise my hand.
Okay, just wanted to check. All right, well, thanks again, Lantao, very much for a nice talk. And next week, we are going to hear from James Head from Brown University.